Welcome to another short and sweet lesson on kinematics. This lesson is going to be about using the one-dimensional kinematic equations, and we're going to use the fact that at Bonneville Salt Flats there's a current record of 602.407 miles per hour for a vehicle on the 11-mile track. We will assume a constant acceleration and that the top speed was reached at the end of the track and the car started from rest, and the timer didn't start until the car was moving. This gives us the following starting facts to figure out the rest of the laundry list. Time initial is 0. Time final, we don't know. So we don't know time. We know the distance initial, it was 0 miles beforehand. Distance 11 miles, of course it's the wrong unit. Change in distance is going to be 11 miles. Once again, the wrong unit. Velocity final, 602.407 miles an hour. Once again, wrong units. Velocity initial, 0 miles an hour. Actually be 0 anything. Change in velocity is that. So what can we figure out from this? Well, let's go for it. First of all, there are 1,600 meters in a mile. 1 hour has 3,600 seconds, 60 minutes times 60 seconds. So we have 602.407. If we multiply them by our conversion, we have 1,600 meters in 1 mile. We have 1 hour for 3,600 seconds. This is going to kill that. This is going to go against that. So this should give us an answer with meters per second, which is the standard SI unit. At this point, pull out the calculator. Hopefully it will show up. 622.407 times 1,600 divided by 3,600, or 276.625, 276.625, we'll call it 276.63 meters per second, just to kind of keep this all in reason. Well, we can do this. So this brings us to this point, and yes, I computed the 11 miles to the 17,600 meters when you're off screen. But now we want to know what average velocity is. Well, we can put up the formula for average velocity here. It's kind of cool, except for one problem. I got two things I don't know. This guy's not going to work for me. So let's see what we can do next. Well, I can understand that velocity final plus initial over 2 is the average, or plug in the 276.625 plus the 0 meters per second, divide by 2. So this gives me an average velocity of 138.313. So we can put this at 138.313 meters per second here, which is what we have this one, 138.313 meters per second. Yes, I've changed colors to show what we actually now have computed, as opposed to before we just doing some conversions. That really doesn't count. So what does this give us on time? Well, start off with our friend, the formula, average velocity, delta t over delta d over t. This gives me delta t is delta d over delta b, average. Shove in a couple of numbers, 17,600 meters for the distance, and 138.313 meters per second, do some canceling meters, and I got 127.248 seconds, or about 2.21 minutes. So time final is 127.248 seconds. It's also your delta, 248 seconds, which then says, okay, let's look at our laundry list. What's left? This acceleration. Acceleration is change in velocity over change in time. Our change in velocity was that 11 miles per second. What do we have? The change in velocity. There we go. 276. So I go 276.623 divided by change in time, 127.248. Over here I have meters per second per here. Time is obviously in seconds, and it is down here. So 1 over that. This will give me a final answer of, let's find out, 276.62325. Divide by 127.248 and enter. Hope it works. 2.26, and it can round down. So 2.26 meters per second squared. If you divide that by the 9.8 on Earth, this is about 1/5 of a gravity. So not quite as a fast acceleration when you average it out. The reality is these guys get up to speed much sooner than that, but that's just the problem. Hopefully that answers this question.